Hello Java 8, or should I say package, playground, public class, sandbox, public static, void main, string array, arg system, out print line, hello Java 8, semicolon. Recently I stumbled upon a classic video by Joshua Bloch where he presents Java puzzlers, and one of these puzzlers, my favorite puzzler, is called histogram. Let's look at it very quickly. Here's the link, or just enter this into Google, you will find the video. Very highly recommended watch. So we have a string array of 4 words, these 4 words. Then we have a main method, and inside the main method we create an array of 5 integers. And then we have a nested for each loop. So word 1 is going to be one of those 4 words in succession, and each time we choose a particular word, we iterate again with a different loop variable. So we should get all 16 combinations for possible word pairs. Okay, here we concatenate both words. So first we get I, then I recommend, I polygene, I lubricants, then recommend I, recommend, and so forth. Then we compute a bucket, which should be a number between 0 and 4. So we get a valid index into this array, and we increment the bucket by 1. And since we do it 16 times in total, we should have a sum of 16. And indeed, this code segment computes the sum. So we start with 0, and for each element in the histogram, we add it up. Okay, so at this point, pair count should have the value 16, and this 16 is added to the character C. So the interesting static type system question is, if I add a character and an int, what do I get in Java? Do I get a string, C16, or do I get a character, which would be, okay, 16 more than C would be D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T or something. So do we get a character, or do we get the Unicode of the character? Something in the 80s range. I suggest you pause this video now and think about it for yourself for a couple of seconds till you figure it out. We could either run it or have Eclipse help us. I can simply click on the print line, and the Java doc tells me which overload of print line was selected. There's an overload which takes an int. So clearly character plus int is an int in Java. Okay, let's run it and see if that prints a number indeed. And it doesn't. Maybe I should make this a little bigger. Okay. Exception in thread main. Java lang array index out of bounds exception -3. Okay, so in line 23, which is here, we try to access a negative index. And this is rather surprising because first we compute the absolute value, so we have a positive number. And then we divide by 5 and look at the rest of the division. This should be a number between 0 and 4. So where does the negative number come from? Maybe we can print out the pair and identify which is the problematic one. Okay. Maybe okay. So here you see the list of words that are generated. First the I words, then the recommend words, then the polygene words. And the last polygene word seems to be the problem. Polygene lubricants. Let me just copy this. Okay, copied. And then I go into JShell, which is a new Java 9 feature, interactive REPL for Java. Can I paste this here? Yes. And let me compute the hashcode. Okay, so the hashcode of this special word is, I don't know if you recommend this number. It's the same number as IntegerMINVALUE. And what is the absolute value of that? Yeah, it's the same value. This may be surprising to you if you don't know how ints work internally. Since int use two's complement, we have this unique situation that you cannot make the smallest integer positive, because the largest integer is ends in a 7 and not in an 8. So there's no way to negate this number in Java. You get a negative number. Okay, and this negative number, if you divide by 5 and look at the rest of the division, it's exactly the -3 that we got. Okay, so there's several ways of mitigating this problem, but those are not the point of this video. The point of this video is answering the question, how did Joshua Bloch find this word? I think he answered this question in the video, or maybe another video, where he said he simply took a dictionary and then concatenated all possible combinations and computed the hash and saw if he found such an interesting pair. And maybe there are other interesting pairs. So the point of this video is trying to write and optimize a Java program for finding polygene, lubricants, and other words that have integer min value as the hash. Okay, so let's create a new class. Let's call it polygene finder, for lack of a better word. Okay. So maybe I start by writing the name of my dictionary. If you want to execute this program at home, you will have to download a dictionary. I have one located at home called English. Okay. Okay, and then let's write a main method. And since Java 7, it is relatively painless to read in a file line by line and get back a list of strings. Let's see, what was the API for that? I think it was files dot lines. Yeah, I think it was, or was it read all lines? I think it was this one. Please don't ask me what's the difference. Okay. Okay, then dictionary. And I think we need to provide more parameters. Let's see if we actually need it or not. It has to do with text encoding. Okay, this can throw an exception. I think that's the first problem, yeah. Okay, let's write a try catch block. So, catch the exception, organize imports. And let's just write that we had problems reading the file. Could not read file dictionary. And maybe also print a stack trace. Just print the exception itself, then we get a stack trace. Okay, we haven't stored it in a list yet. Let's do that. Let's call it words. Okay, and then just let's try to see if it worked. I think we will get some sort of exception due to character encoding. Yeah. Okay, what does it say? Could not read file input length like one. This is a very curious error message. If you ever get those, you have a problem with character encodings. So it should be, I think, char set for name. Was it this one? I think. Let's see if this works. Okay, this looks better. Okay, this is some sort of error in how Eclipse displays the console. Let's stop the program. Maybe if I scroll a bit it will disappear. Doesn't seem so. Okay, maybe we will just print it line by line, or the first 10 elements or something. Let's write out the first 10 words. Classic for loop. Hopefully nothing too complicated. Okay, just to see if it works and what the words are. Okay, so you can see apparently the dictionary orders them first by length and then inside words of the same length by alphabet. Okay, why not? I don't particularly care. Okay, just for fun, we don't need to write a for loop. You could also get a stream, then limit the stream to 10 elements, and then print it to the console. So no loop, no manual loop, no variable updates. We all love this in Java 8. Should be the same output. Yes, exactly the same. Okay. Okay, so this works reading lines from a dictionary. So what do we do next? Maybe I'll call another method at this point. This try catch is already large enough. Maybe let's call it analyze word pairs or something, and pass words into this method. Doesn't exist yet. Let's create it. Okay. Well, and inspired by the histogram program that we saw, we can simply use a doubly nested for loop, build the string, and then simply check the hash code. This should be rather simple. So let's call it maybe A for the left, or maybe left for the left word. Okay, and then again for the right word. And then we will simply concatenate them. Pair equals left plus right. And then we'll check the hash code if it's one of the interesting ones. If it equals integer min value, we have a winner. Oops. What's the problem? Missing closing parent. Yes. We have a winner. Let's just print it to the console. Okay. This is all that is required to find all the interesting candidates. The problem is, if we run this, yeah, you see the cursor is blinking and nothing's happening. It simply takes a very long time to build all the word pairs, concatenate them, compute the hash code. This is basically an ON squared operation. Okay. Since our goal is to make this program faster in several steps, maybe we should think about measuring the performance. Okay, so maybe write a utility class, let's call it timer, and we'll write a static utility method. Let's call it measure. We give it a job to run. Okay, and then I don't know how you time your Java code. This is very, very crude. Let's just say we start at whatever time is now. Then we run the job. Then we look at the clock again. Then we compute the difference. Okay, and then we get a result in nanoseconds, which isn't very interesting for things that take seconds or maybe even minutes, I don't know. So let's first divide it by, to get seconds, by 10 to the 9, I think. Okay, and then we'll simply print it to the console. What do we print so we know what it means? Maybe simply seconds plus the string seconds should be informative enough. Okay. Okay, look at the clock before we start. After it has finished, compute the difference. This is a positive number, yes. Divide by 1e9. Yeah, makes sense to me. So back to the polygene finder. And now I want to pass essentially this code as a runnable to the timer. So how would we do this in Java 7? We would say timer.measure runnable job. Now we would say new runnable. Can I somehow autocomplete this? Yeah, anonymous inner type. Right. Okay, and then we would say, we would simply move this line here. Okay, let's just delete this line, we don't need it anymore. This is the Java 7 way of doing it. Anonymous inner class, not very nice. I think Eclipse can convert this automatically into a Java 8 lambda. If not, I'll do it manually. Let's see. How would I do this? Refactor. Refactor. Okay, I don't see it here. Maybe I have to do it here. Refactor. Okay, I don't see it. So let me do it myself. We need the parameter list, then the lambda arrow, and then what we want to do. And since it's only a single expression, we don't even need the semicolon, and the rest is boilerplate. Yeah, okay, this should work. So what I'm going to do now, I'm going to start this program and pause the video, because this is going to take several minutes, I suppose. So I'll see you soon. Okay, so the program finished. It took 1,360 seconds. Let's do a quick check how much that is in minutes. Okay, about 22 minutes. This is not very attractive. I think we can make this program faster. So what are some obvious problems we can fix? This is a very interesting line. Why do we compute the pair? Why do we concatenate left and right? Because we are interested in the hashcode. And the question is, can we compute the hashcode of this string without actually building it in memory? Because as you can imagine, you have to create a new object, you have to copy the characters over. If I'm not mistaken, you even need a string builder in the background for that. So this might be quite an expensive operation. We'll measure later how expensive it really is. So we need to understand a little bit how hashcodes are computed in Java. So let's look at a couple of examples. For example, the empty string has, hashcode 0. And if we have a string of only one character, the hashcode is the Unicode of that character. If you don't believe me that B has the Unicode 98, we can simply convert it to an int and it should be the same number. Right, 98. Okay, how about longer strings? For example, B, to be or not to be, has larger hashcode. So it's not like we only add the Unicodes together. That would be something about 200. What happens is instead is that the first character is multiplied by 31 and the second character is added in. Right? That's the same value. And if you have even longer strings, it works the same. So you multiply by 31, add the E, then you multiply that by 31 and add the N. This should be 97,000 something, right? And we can maybe one last example with 4 characters. Again, I could type an expression that is somehow like this, but I would like to think about this string as a concatenation of B and nd. So let's look at the hash codes of those. Okay, suppose we know the hash code of B and we know the hash code of nd. How do we compute this hash code? So we saw for each additional character, if we append E, we first need to multiply by 31. And if we append the N, we first must multiply by 31. So depending on the length of the right string, we need to multiply the first hash code by 31 so many times. Okay, let's do this. So B hash code multiplied by 31, multiplied by 31 again, because nd has length too, and then add this together. So what do we expect? We expect this number, which is 3 million something, and there it is. Okay, so we don't need to concatenate the string, build the new string in memory, and then call hashcode. If we know the hashcode of the two strings and the length of the second string, we can compute it ourselves. Okay, so how do we compute 31 times 31 times 31 n times? You might be tempted to use the pow function, right? We have, for example, 31 times 31 is 961, and math.pow 31.2 is the same value in double, but this will break down very soon. I think 31 has 5 bits, and int has 32 bits, so above 6, it should give different results. So let's multiply it 6 times. Is this 6 times? So this should be the same result. Right, it is just a weird notation. And if we do it again, we should get a quite different result. Right, these numbers have nothing to do with each other. Okay, so this function will not work. I would suggest we write a lookup table, an array which contains the powers of 31. Maybe we should write a program to compute this for us. So let's go to the sandbox and maybe write a simple for loop. Let's start with 1, because 31 to the power of 0 is 1. And then I don't know how many powers we need. Maybe, I don't know, hopefully 64 is big enough. We print, and maybe we print the number followed by a comma followed by space. Which number do we need? We need x, and then we multiply by 31. Okay. Let's see if this works. Right, we recognize these 3 numbers as being correct, and then we see here it starts to get funny because we get overflows. Okay, but this is exactly what we need. The same overflows happen inside string hashCode. Can we do it without the for loop? This is Java 8, not Java 7. Let's see. We can use an int stream. Is it automatically imported? No, it isn't. How to import it? Okay. And we can use this factory function. I can start with an initial value, which is 1 in our case, and then a lambda function that says we want to multiply by 31 each time. So for each x we get in, we want to multiply by 31. Then we have an infinite stream. This is a little bit too much. Let's limit it to 64 elements. Okay, and then we can do the printf, or we could convert it into a string. Maybe that would be a little more interesting. So let's map the values to strings. I think there's a function string value of that takes an int and converts it into a string, right? This is not the one I'm interested in. String. Can I jump into the function? Maybe because there's a syntax error. Right, here's the function. Takes an int, converts it into a string. Okay, now I have a stream of strings, and now I want to join them into one string. Why do I have an error here? Is this an Eclipse error? Oh, I already have a variable x. This is, let me just get rid of this code. I don't need it anymore. Okay, and now I want to join those. I can simply collect. This means I want to leave the realm of streams and want to get back into collection land or string land or whatever. And how do I import this one? Collectors joining. There it is. Joining with a comma. Okay, this fantastic expression is a string. Let's assign it to s. No, I want to call it s. Okay, so it fits on the screen. And then we write it to the console. This should give us the same result. Let's see. Right. We recognize 1, 31, 9, 61, and then the strange overflow here. And another benefit is we don't get a comma at the end. I didn't show you this. The for loop generated 64 commas. This will only generate 63. So if you ever had the problem of concatenating a list of strings and put commas in between but not at the end, this is exactly what you're looking for. And I like to import joining statically. Oops. Because then it simply looks a little bit nicer to my eyes. Collect by joining with comma. Okay. Whoops. Ah, right. You may find this a little bit more readable. I just formatted the source code so that each step is written on a single line. This may be a little bit intimidating. Very long line, really hard to discern where one process starts and stops and another one starts. But if you format it like this, I think it's quite readable. Iterate starting by 1, each time multiplying by 31. This is kind of what you would, the loop logic. This is the loop logic if you want. This is where we want to cut off the infinite stream. Here we convert to strings, and here we join with commas in between. I like this style of programming. Okay, now we can simply copy this entire thing and use it as an initializer for an array. Let's call it powers of 31. And then I paste the numbers. Okay. Auto format. Okay, why? It's not a string. It's an int array. Right. So we have our little lookup table. So we can compute power of 31 to an exponent very fast without loops and such. And now we go back here. Our goal was not to compute this string, but to compute the hashcode ourselves. So we said left hashcode, and then multiplied by, hello, why is he not, that's right. And now how many powers of 31 do I need? Or how many 31s do I need? It depends on the length of the right string. So we have the length, and then we add the hashcode of the right string. In case you're confused now, this is exactly what we did. Where did we do it? Here. This is exactly what we did here. We computed the hashcode of the left string, multiplied by 31 to the power of the length of the second string, and then added the hashcode of the second string. Exactly the same thing, just abstract, not concrete example. And I need to assign this to a variable. Let's call it hash. Is this okay? Yes. And then we can simply check if that's the hash we're interested in. Oops. And then we can print it to the console. Left plus right. Oh, yeah. Okay, this should work. This should be somewhat more efficient. I don't know how much more efficient. Again, I'll stop the video and we'll see how long it takes. Let me start it, wait for a couple of seconds, and then stop. Okay, what a pleasant surprise. Not even 2 minutes. So we get a speed up of about 1 order of magnitude, about factor 10. This is quite pleasing. So simply by not computing the string and then the hashcode, but computing the hashcode directly, we saved a ton of work for the Java virtual machine. Right, so millions of strings that didn't have to be computed first. Okay, so maybe in practice this is already fast enough, but let's see if we can make it even faster. So the word that Joshua Bloch found, the polygene lubricants, let's play with that a bit. So we have these two hash codes. Okay. So what happens in our program in this loop is when left is polygene, we scan the entire dictionary looking for a word that fits. So we have all these words, a couple 100,000 I think. We compute all the hash codes, and then we compute the combined hash code and see if it's the one we need. The interesting thing is, if for a moment we imagine that all words had the same length, obviously they do not, because even those two words have different length, but let's just imagine all have the length 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then we would multiply the left hash code by 31 to the power of 10 and add the right hash code and see if it's the one we need. Okay, so we would say polygene hash code. Okay, I don't have I don't have the array here, so I have to do it myself. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, What is this intermediate result? Okay. And now if we add this number, we should get the integer min value. Let's see if this really happens. This is $26 plus $25. Right. So the interesting point is when we know this value, then we know what other hash value we are looking for. We are looking for a word which has this hash value. All other hash values would not fit. Okay, so right, this is simple arithmetic. Instead of adding and seeing if we have the value that we need, we can simply subtract from integer min value the value that we already have, which is this one. Right, this is the hash code that we are looking for. For example, lubricants has this hash code. So if we had a data structure that could answer the question, hey, is there any word that has the hash code -5 whatever, and it could quickly say yes or no, then we wouldn't need this second inner loop, right? We could directly ask the question, which word has the hash code -57 whatever. Okay, the only problem with this approach is that we multiplied by 31 to the power of 10 because we knew that this word which fits has the length 10. In practice, we have to do it for all possible lengths. So we need a data structure that, given the length of a word and a hash code that we're looking for, gives me the word that I'm looking for. This may sound a little bit abstract, but hopefully with code it'll become clear. So how do we build this data structure? We could try it in Java 7 first, but it would be lots of code because we have to build a hash map ourselves basically. So let's do it in Java 8 directly. So let's start with a stream. Okay. And now I can say to the stream, hey, you have all these words, 150,000 whatever words. Please group them by length. Let's do this first. Group. Oh, I can't. It's a collecting operation. I always get those confused. Collectors grouping by. There we are. Grouping by the length of the string. Okay. This is just the first step, and I want to show you how that looks like. What we get back by length. So we start with a list of strings, and this grouping operations gives us a map from integer to list of strings. For example, it will map 1 to the list of all words which have the length 1. We can see if this is indeed what happens. What is by length get 1? This shouldn't be very many words, maybe 1 or 2. I and A, I don't think there are any more. Let's see what happens. Right, I and A. What about lengths of word 2? Words of length 2. Right, I have no idea what these words mean. Most of them I've never seen. This is a word I recognize. This. Right. What about maybe words of length 3? Okay, well, you see we have a list of words of length 3. This should be somewhat understandable. Let me again do a static import. Grouping by, where did I import this? Here are the collectors. Let me just import grouping by statically. Okay, then I can write it a bit shorter. Right. And now I want to group each list again by the hash code. So I want, maybe I have some collisions in here. I think it's quite improbable, but maybe. Let's do it and we'll see what happens. I can simply group again the result by string.hashcode. Okay. And now let's name it maybe by length by hash. This is a somewhat meaningful name. I have no idea what happens if I now do auto format. Let's see if that makes it a little bit more readable. Oh yeah, fits on the screen. Okay, so by length by hash, and again maybe at 3, I would expect now to see a map of all words of length 3 grouped by the hashcode. Let's see what this looks like. Here we are. So there's exactly one word that has the hashcode 98,307. This one, egg has this hashcode, iron has this hashcode, ego this, and so forth. I don't think we'll have enough luck to see any collisions here, but trust me, if several words had the same hashcode, you would get collisions. Maybe if we pick a longer length, I don't know, maybe 7 or 8 is more likely to have collisions. But again, I don't think we have enough luck to actually observe it. No, don't think so. Okay, but this is the structure. I hope this is clear. Again, let's revisit what we've done. First, I grouped by length. So this means I get a list of integer key type. And then I grouped again by the hashcode, which is also an integer. And these lists contain words which have the same length and hashcode. And this is the important part. Okay. So in our example, we said let's only do it for words of length 10. And now we have to do it for all possible lengths. And we can simply ask this map, hey, let me just iterate over all your keys, basically. Okay. Right, so where will I put this code? I don't need this code anymore. Let's comment it out. Later delete it. So I want to iterate over this map. So I can access the key, which is the length, and this map. Okay, how do I do this? In Java 7 you can iterate over entry sets. In Java 8 it's a bit simpler. I can use the for each method. Right, and the for each method accepts a by consumer because the lambda that I now pass in must accept the length and the map, the key and the value. Okay, the key is again the length, and then we have the let's call it by hash map. Okay, and then the body. Let's put it in this line. Okay, so the first time. Oh, why is this an error? I forget to close this parent. Okay, so the first time we enter this loop, length will probably have the value 1. And I have access to all words of length 1 organized by the hash. And the second time I enter the loop, length will have the value 2 and so on. Okay, so I can take the hash code of left. And what did we do in our concrete example? We multiplied by a power of 31 depending on the length of the second word. And the length of the second word is exactly this parameter. So I can multiply by 31 to the power of length. Okay, let's assign this to a new variable. Oops. Well, sometimes you have to write stuff by hand or it gets funny. Let's call it, I don't know, like this. Okay. That was this part, and now we have to compute how far away are we from integer min value. Okay, I can do it in one step. Integer min value minus this, and let's call it maybe target hash. Okay, so now we have computed in effect this number. We've computed this number, and we have to look into the hash table if there is a word of the correct length and the correct hash code. We don't need to check the length, we already have the right hash map here. Now we have to just see, do we have a word with that hash code that we just computed with this target hash code. So by hash, get target hash. Let's call it writes. And again, we could have collisions. I don't think in this example we will ever have collisions at line 50, but potentially we could. But this list could also be empty, right? Maybe there is no word with such a hash code. So only if it's not null, we will iterate over the list. And now we have found exactly what we're looking for. So let's print it out. Left plus right. Okay. And before we start this, let's again think about why we expect it to be faster. So the outer loop is exactly the same, okay, but we now no longer have an inner loop. Okay, we have an inner loop, but it's very much shorter. The inner loop that we used to have ran 150,000 times for each word, and the inner loop will run maybe 30, 40 times. I have no idea how many different lengths there are in a dictionary. I suppose no English word is longer than 50. So let's just say this loop runs 50 times, not 150,000 times. Okay, and what do we do? This is just some arithmetic, shouldn't take long, and then we do one lookup, which should be constant time. And then a simple if. So I would expect this to be dramatically faster. So before we had, I don't know, 2 minutes, 107 seconds if I remember correctly. I'm not going to bother stopping the video. It should be below 1 second. Let's see what happens. Right, third of a second. Let's run it again. Yeah, 0.3 seconds. So this is again 300 times faster just by eliminating this one loop, which is quite impressive, I think. Okay, let's get rid of this code. We don't need it. Can we get rid of this null check? I really don't like having to assign the result to a variable, check if it's null. If it's not null, I can loop over it. Is it somehow possible to plug this expression right here and get rid of the check? So of course we would expect to immediately get a null pointer exception. Just let us verify. Yes, this should be a null pointer exception. There we are. So how can I tell the map if you don't have an entry? Give me an empty list, for example. There should be a way to do that. Let's see. Ghetto default, this one. Okay. So if you don't have a value that belongs to this target hash, give me, for example, the empty list, collections.emptylist. Okay. So anything wrong with that? Maybe missing parent again. Right. Okay, is this substantially slower? We have no idea how expensive it is to create an empty list, and this for loop has to check if there are elements in this empty list. So before we had 0.3 seconds. What about now? Yeah, it's basically the same. The difference we observe now is probably noise. And I find this is a lot more readable. Don't know about you. I find it more readable. Okay, 0.3 seconds. Can we get this any lower? How about the outer loop? So we process 150,000 words one by one. How about we do this in parallel? So that would be replacing this loop by for each invocation. So, and now we need to close the parent about here. No, what did I do wrong? What is he complaining about? Syntax error. What's wrong with that? Oh, of course, I already had an opening brace. That's quite embarrassing. Okay, depends on your style if you put the opening brace here. I used to put it in the same line, and a couple of days ago I switched to putting it in the next line just to be consistent with the old Java 5 for each statement, and now I was a bit confused because I put it in both places. Okay, this is still serial. Let's see if it slows down noticeably. No. Basically the same result. Now let's do it in parallel. Oops. And see if we get... I don't expect much performance improvement because this is below 1 second and you get some overhead I would expect. I think I have 4 cores. Maybe we get twice the speed. I don't know. I'm not a performance expert. No, it's rather disappointing. The speedup is not very significant. You may find in other problems, or maybe if your dictionaries are larger, that you will get more significant speedups from doing a parallel stream. Okay, but let's remove this for once. If we run this code, how long is the list of... We never looked at the words. Oh, it's not so many words. It's just 1, 2, 3, 4, 5, 6. And here are the polygene lubricants. So we rediscovered them again. What is the order? Is this somewhat ordered? Q, P, S? Oh, not really. Maybe we should order the input list, or sort the input list first, because it's sorted by length. Words dot sort. All right, I have to give a comparator. This is a confusing API. Why is there no overload that takes no parameters? Okay, let's run it again. Now they should be in alphabetic order. Right, B, P, Q, R, S, T. Okay, so this is worth mentioning. If you replace serial loops by parallel loops, you will get basically non-deterministic order. So every time you run this, you can get, right, for example, T comes before P now, then S and R before S, and Q before R. So basically, what I imagine what happens is 4 threads are run in parallel. One starts with the first 25% of the dictionary, the next with the next 25%. But I've never really looked into this. This is just what I imagine. Okay. Yeah, I think this is all that I have. So we started with 22 minutes. Then we got it down to about 2 minutes, then 0.3 seconds, and then by parallelizing, we got another maybe 50% performance increase. But the nice thing is parallelizing was rather trivial. So all we really did was in this parallel stream statement. Okay, now that it's possible to find polygene lubricants quite fast, maybe you can do it in your own language. All you have to do is download a dictionary in your own language, run this program, and maybe you can share some funny polygene lubricants in your own language with us. With that, I'm going to quit undistressed and say goodbye.